Good morning, everyone. Thanks for coming in on this beautiful morning. Welcome to day 2 of ATVA. My name is S. Akshay. I'm a professor in the Department of Computer Science and Engineering at IIT Bombay, Indian Institute of Technology, Bombay. And it's my great pleasure to welcome Anne-Kathrin Schmuck for her keynote, the second keynote of ATVA today on the power of feedback, rethinking reactive synthesis in cyber-physical systems. Before we get started with the proceedings, let me give a short intro of Anna. And Anna is a tenure-track faculty member at the Max Planck Institute of Software Systems at Kaiserslautern in Germany, which is the leading control systems group. And she's a member of the ME Noether program of the DFG since 2020, and her independent research group was hosted at Max Planck at Software Systems until she became a faculty member in July 2023. She studied at various places in Magdeburg in Germany, in Vancouver, Canada, and Sweden, and she received her PhD degree in electrical engineering from TU Berlin. Thanks, Anna, and we look forward to an engaging talk.
Hello, that sounds better. Yeah, thank you for inviting me. I'm very happy to be here and tell you a little bit about the things that I'm excited about in research, which, as you can guess, center around feedback. And I'm not sure if you've seen this, but about 10 years ago, the newspapers titled that self-driving cars will be everywhere in 2020. But I'm not sure if you've noticed, but I would argue that didn't really happen in the scale it was anticipated, right? And at least I'm still driving my car all by myself. And how do I do this, right? Well, I perceive the environment around me. If the traffic light is red, I brake. If there is a slow car in front of me, I take over. And in all these decisions that I'm making, I'm keeping my goal in mind, right? Whether I need to pick up my kid or go to the supermarket or go home. And with this long-term goal in mind, I take these decisions at the moment, and then, I accelerate, I brake, and I navigate traffic. So I interact with my environment and feedback. And I'm not just doing this for driving. Indeed, feedback is the fundamental principle of life, right? It lets animals breathe, it stabilizes the climate, it allows birds to fly, and humans to learn. And in the beginning of the last century, during the Industrial Revolution, people have realized that in order to build trustworthy, performant, and reliable technological systems, we have to copy nature, and we have to build software that interacts with its environment and feedback. And this software is called a controller. And controllers are literally everywhere in all the technological devices that we're using. They stabilize, or they regulate the temperature or the water level. They are the fundamental principle behind automatic cruise controller. And more importantly, they are extensively used in safety-critical applications. They stabilize the energy grid and make sure it operates reliably. And I don't know if you know that, but the breakthrough in making airplanes fly was to figure out how to stabilize unstable dynamics by a feedback loop that allowed people to really maneuver airplanes safely in the sky when they were developed. And feedback control has brought us a long way, right? So currently, if you look at robotics, we have robots that just not walk, they run like humans, and this is powered by sophisticated nonlinear control that makes sure these guys don't fall over. And here we see inspection robots of an oil pipeline in Norway, and they're powered by nonlinear control to make them flow like snails in the water, almost effortlessly without much energy consumption. And this is not just true for individual systems. If you look at these ant robots, they're running a decentralized controller for adaptation that builds in a field that makes them attracted to a light source like this one and makes them repellent to all its surrounding ant robots, just like a swarm in nature. And this is decentralized running on all these devices and generating an emergent behavior of the entire swarm. And finally, you all know an adaptive cruise controller. You turn it on, it keeps the distance to the lead vehicle and a certain speed. And by that, it really makes sure that you're running safely on an autobahn. And much beyond the performance of any human driver, because it always pays attention. It always makes sure that you don't collide. So if feedback control is so powerful, why doesn't feedback control simply enable us to build trustworthy autonomous systems, such as an autonomous car? Well, there is a lot of feedback control in a car. The most prominent example, as I showed with the video, is an adaptive cruise controller. And this adaptive cruise controller regulates a physical quantity, like the speed or the distance to the lead vehicle. It monitors this quantity instantaneously all the time, and it instantaneously adapts its actuation variables, which is the speed. So it actuates the gas pedal and the brakes inside the car continuously all the time. And by this, it smoothly adapts the performance of the vehicle to its set point, and independent of how fast the car in front of it goes, how many people are in the car, what type of road you drive on, and so on. But if you want to automate driving, there is another feedback loop that you have to care about. And this feedback loop I usually call a symbolic control loop. And it's not that instantaneous, but it's still a feedback loop, because you have to figure out the context you're driving in, whether there's a car in front of you, whether the traffic light is green or red, and so on. And you have to react to it by making decisions on whether you brake and whether you turn. And the right decision, it might be instantaneous in case of the traffic light, but it might be driven by long-term goals as to where I want to reach and where I want to go. And then I take a decision to turn now, but maybe I have to turn again in the next intersection because there's a traffic jam or there's congestion, right? So there are disturbances on that I have to perceive, and then I have to react to them on a much longer time scale. And these decisions that I'm taking, they're actually actuated by lower level control, because if I decide to turn, I actually have to actuate my vehicle to do that. And I want to call these things physical symbolic control loops. And I want to make the claim that if we want to get trustworthy autonomy driven by feedback control, we have to automate. We have to build or automatically design, correct by design, physical symbolic control loops. And this is not what we have today. If I drive my car, I turn on my automatic cruise controller. If I run on an autobahn and it's working perfectly fine, it's almost autonomous driving. But if I go to a dense city traffic, I rather turn it off if I have to take a lot of decisions, because I rather have control over my vehicle all by myself. Or if you think of air traffic control at an airport, there's lots of continuous control loops powering an aircraft, but when it comes to deciding which airplanes lands and takes off on which lane, this is done by humans. Exactly, like one human is assigned exactly 6 airplanes, and they make sure that nothing goes wrong. Similarly, if you go to the energy sector in a nuclear power plant, or also in the energy grid, if you think of high-level control, there are fixed profiles that they've run in order to bring these systems to different stable points, or to mitigate disturbances from renewable resources. And this is far away from being automatically reactive. So there is something fundamentally hard in these problems. And this is also somewhat surprising, because control engineering has been there for decades. And we know how to build certified physical control loops. But we also know how to build certified symbolic control loops, and Orna has talking about this very nicely yesterday, because all these things that I described here are just open systems, right, that have an event-driven behavior and that you want to react to in a reliable manner to fulfill a specification. And I'm not the first one who observes this. This observation was made about 2 decades ago, and it has triggered a lot of research in this intersection of reactive synthesis or formal methods and control. But I would claim that all the approaches, or almost all the approaches that are out there, either make the whole problem look green by actually taking the specifications, like LTL, mapping them as constraints into an optimization problem. And this is really nice because you can use the framework of control to to address all the engineering implications of what you're doing, and that makes these control loops very attractive. But if you do that, then you can't handle logical inputs. You have to think about the high-level control loop as a closed system, and you can't make that reactive on a higher level. If you make the whole problem look orange, there's a lot of work in this, but then you have to discretize these physical dynamics to make them look like an automaton, and then you lose all the power of the physical feedback loop to address the engineering implications, and then you have to do a lot of acrobatics to get it back in. But I would claim that these 2 disciplines are good in what they're doing, and I think we have to use the power of feedback to let them do what they're good at and try to figure out how we can build a certified interface between them so that they can interact in a feedback manner and get us to really performant and trustworthy systems. And for this, I have been working on rethinking reactive synthesis for this purpose in order to address these engineering implications that come from the orange side that have not been looked at so much in this control context of reactive synthesis. And in this vein, and I also going to talk about not just a single system, but multiple systems that are interacting on both layers. Okay, so much about the motivation. I hope you're excited now to hear what we have been doing. And I first want to convey to you the core idea of the work that I've been doing in the past years, which are called strategy templates. And then I want to show you how we use them to integrate physical and symbolic control in a novel manner, and then how we also address the problem of distributed control from a different angle that was motivated from these control applications, and then I'm gonna conclude. Okay. So let us start with permissive strategy templates. Okay, so let me open up this little box for you. So we have a symbolic context, we have symbolic controller, and let me give you an example. So in the back of your hand, you could think of robots that are packaging products into different boxes, right? They're arriving on this conveyor belt. And now the context here is really, what type of object arrives at the conveyor belt and so on. And if there is a box and how many boxes are there and so forth. The logical specification tells you how to pack these goods that are arriving, right? And there are multiple robots, they cooperate in packaging, but currently we're only looking at one, right? And what we want to do is I want to show you how to model these problems with in the classical framework of reactive synthesis via games, and what's special about this compared to classical reactive synthesis. And then I will discuss the concept of permissive strategy templates and show you why I think they have preferable engineering properties for this control task. Okay. So let's do that. So in order to explain that in a bit more depth, I will radically simplify the robot packaging example into one that is so simple, okay? So let's assume we are controlling the blue robot, And we are not modeling the packaging or anything. We're just modeling that it has to go to this upright corner here repeatedly to pick up things. And then it has to bring it back down here to package it. And I'm sorry, there is a light gray background here and here that's not very visible in the slides, but this kind of signals the specification. And to argue why we want a reactive controller here, there is a robot in the environment that also has some task that we don't know and that we don't model, but we actually have to avoid it, right? So we shouldn't bump into it. And to make the problem realizable and to make everyone happy, let's assume that we know that this robot is always moving if there is a possibility to move, okay? Just for illustration purposes. And now in this, if you look at this picture, then what does this say? So the context here is really where these robots are positioned, okay? And the observation that this blue robot makes is essentially observing where this purple robot has moved, okay? And at the same time, the controller that is controlling the moves of the blue robot also changes the context by moving itself, right? So this is this loop right here. And then there can be disturbances that we don't model. And in this simple example, the disturbance would be that a human steps into that grid or something, you know, is placed there, and a certain box cannot be traversed, okay? And in the logical specification here is that this blue robot has to visit these upper right and lower left corner infinitely often. And in a classical reactive synthesis problem, you would put all this into the specification, but I would want you to think about it from a control perspective. In a control perspective, what you do is you have a nominal model that captures the physics, and then you design a controller that limits that possible behavior to all the desired traces. And we also do this here, right? So in this context, we kind of model the physics of the problem that we have as the game graph. And then we interpret the specification over that game graph in order to limit the behavior of the system that we are controlling. Okay, so keep that in the back of your head. It will come back over and over. And to illustrate this, let us build a game graph that's associated with this problem. Okay, so the environment starts by parachuting itself somewhere. Let's just say it's parachuting itself here. We are located here. We own this vertex. We can make a move. And our move can be to stay where we are or to move to the only cell that we can if we are not want to bump into a wall. Now it's the environment's turn here because we assume that it always has to move. It's moving. Here it can't move. So it just stays where it is. Now it's our turn again. We ignore this upper vertex for the time being. We expand only the lower one. Right, and here we can either stay where we are and give the control back to the other robot. We can go back to where we came from, or we can move up, or we can jump on the obstacle. And of course, this is not allowed. I just put it here for illustration purposes. And then we keep going and going and going. And then at some point, you see that if I expand this further, I will end up here. Okay? So this is essentially, and you know, this is going to be a big game graph that captures the physics underlying the problem. And now I put my specification on top. If you're a reactive synthesis person, you know that I can take an LTL specification, automatically transform it into a game, and then you can take the product, and that's all doable. But in most control applications or control people tend to use reactive synthesis in a much simpler way by just saying, oh, I know my dynamics, and now, because my specification has some physical interpretation, I can actually interpret it on that game graph directly. I don't have to go and do a detour. Let's do that, right? So let's say our specification for simplicity is to reach here, okay, infinitely often. And now, I shouldn't jump on the other robot. Okay, that's my safety specification. And if you're used to games, then you might see that if I'm in this node, the environment can move up and then, cycle here forever. So it can prevent me to get to this node when I'm here, right? If I would expand it this. If you don't see this, just believe me that this is gonna be a bad state because it doesn't allow the blue robot, or it allows the purple robot to prevent the blue one to reach that state, okay? Because this is a game, and then if you backtrack this is also a bad state, okay? So somehow, this is how synthesis proceeds. You model your game graph, you interpret the specification on top of it, and then you get things you want to reach and things you want to avoid, and that's a simple specification. It also works for parity and other things, right? But for the purpose of this talk, that suffices. Now, what you do in reactive synthesis is you synthesize a strategy for the blue player. What does this mean? Well, you choose an action in every state that's owned by you. Here, this would be this transition, and then there would be more here that ensures that no matter how the purple robot plays, you reach that goal state. Right? And now imagine that I've done this, and this is what's done if you use reactive synthesis for control. But now, imagine I have a disturbance, and my disturbance is that a human enters the scene and stands here for a little while. And that means that the action I have chosen is invalid. And now I don't know what I should do, because maybe waiting here and standing here makes the other robot win because he can now move along and block my way, right? So it's important to know what my options are. And if you stare at this game for a little bit, you see that the options are somewhat clear, right? You shouldn't go here, and you shouldn't go back, because if you go back, then you might lose, okay? But actually staying there is fine. Staying there is not a problem at all. So you could actually wait here, and once that transition that is green, which is the one you should eventually take to reach the target, becomes available again. And you can also do that here. Here it's less interesting because there is only one option. But you can essentially do that for every node that you own. And this is what we call a strategy template, and that's essentially it. The theory behind it is a bit more rich because we have these live edges, these are the green ones, and if you know LTL, you can read this. If you don't, the intuition is just if you see that vertex infinitely often, you should take these transitions infinitely often. And then you have unsafe edges, which you should never take. And if you want to handle the full class of omega regular games, then you also need co-live edges, which are Kobuki edges, if you wish. And this is swapping things under the carpet. You need groups here to be fully expressive and so on, so groups of states with groups of edges going out. But for the purpose of this talk, this is not important. You can always under-approximate the set of winning strategies by just local templates per state. Okay, and this is what we call a strategy template. It's permissive, it retains almost all winning strategies. It's very simple, it localizes all your choices. It's expressive in the sense that we can do this for parity games, which are canonical representation of all omega regular games, so you can handle LTL as a full class. And the nicest thing about it is it doesn't add any complexity. So you can use the standard algorithms you use for synthesis, and you just do sophisticated bookkeeping in some sense. You have to be a bit careful. So you could, in particular for parity games, use the quasi-polynomial algorithm, but this is not the most efficient. So what we actually do in synthesis is we use a Sri-Lanka type algorithm and massaged it a little bit, but you don't pay an extra price. So the message you can take home is strategy templates are as easy to compute as strategies, but they give you more information locally. And this works for all games that have memoryless winning strategies. If you need memory, then you have to be a bit more careful. Okay, so let me tell you a bit about the engineering properties, why I think permissive strategy templates give you more than a single strategy. The first thing I already hinted on is if this transitions is temporarily procced, then you know what you can do in the meantime. But of course, if this is your only option and this wouldn't be there, then you get a conflict, and then you actually risk in not winning the game anymore if you can't take this. And similarly, if that fault would be persistent, then also you would not be able to win in this game. And these things are called a conflict, right? So if the local changes you have to make to your game graph invalidate the template, so it doesn't give you any winning move anymore. And what we did is we run this over 1,400 benchmark instances we took from the sitcom benchmark, and we randomly inserted faulty edges. And what you see here is that the percentage of vertices that get a conflict in the game is very, very low, even if you have a lot of faulty edges. And from an engineering perspective, these are the edges that you should really protect if you want to use this for runtime adaptation, or you have to resynthesize. But in some sense, this shows that you can do this. And the nice thing is that even without these experiments, we have a linear time algorithm to detect which edges are the ones that really shouldn't be persistently blocked. And you can make sure that this doesn't happen in an engineering application if you understand which transitions are affected by this. The second thing I want to show you is more on this right side. So here we have used a single specification, but you could think of examples where you have a specification and then another specification is added later in time, and another specification is added, and maybe one specification is removed, and so forth. And this is called incremental synthesis. So you're adding more and more specifications. And the nice thing about templates, because they're local, right? So the other thing, okay, what I have to say here is that we assume that the game graph comes from modeling the physics. So this is the fundamental assumption that you have to put in. So your game graph is fixed, and your specifications are interpreted over this game graph as a specification that allows for memoryless strategies. So, for example, ubiquity or parity, right? So these are parity specifications interpreted over the game graph that you have. And then you can synthesize a template for all of them, right? So for the first specification, I have a template per state. For the next specification, I also have a template per state. And now you see how this is going, right? I just take the intersection, I have a new template, I'm happy. Of course, this is not always that easy, right? It could happen that I have a conflict because this is my only winning transition, whereas here this is unsafe. So in order to resolve this, you have to make sure you never visit Q, and that's not a local property anymore, you have to resynthesize. But the nice thing is, so we have been trying this again over a large set of benchmarks from a SynCom benchmark suite, and it rarely happens. You rarely have to resynthesize, you rarely get a conflict, even if, you know, this is really, you know, everywhere that these parity specifications are complex and everywhere in the game graph. So we have been competing against Gensel, which is a dedicated solver for generalized parity games. And that always resynthesizes the entire problem if a new specification comes, but it's a targeted solver for this class of problems. And we are blue, and you see the more specifications we get, the better we get, because we pay less time by just resynthesizing one template for the new specification and then just intersecting. This is one thing. The other thing is we're not complete. Okay, so you can come up with very small examples where this local change rules out strategies. But in all these 1,400 benchmarks that we have been trying here, so this is the average runtime, we always computed the full winning region, so we never lost any vertex. So I would claim it's practically complete over the benchmarks that we have tried. Okay. So these are permissive strategy templates. And let me discuss a little bit how we have used them in the remaining time of the talk. So the first thing I want to talk about is what I started with, this combination of physical control and symbolic control. So again, let me open this up for you. You have a physical control loop with physical observation and disturbances. Think of an adaptive cruise controller. And you have the symbolic control loop And you can think about this as this packing specification. So, for example, you can think of a drone that helps packaging products that has non-trivial dynamics to control. And now I want to show you that these strategy templates allow us to have a new integration of physical and symbolic control that retains certification and exploits this adaptability. And I unfortunately do not have a lab yet where I can fly drones, so I can only show you a video with very boring turtle bots, but you can use your imagination and think about them as drones, okay? So what we did is, this is our office space at MPI, and we have a little turtle bot here that is running our automatically synthesized controller that has a physical and a symbolic control loop here. And this is our environment robot that we remote control, okay? So there is a human controlling that guy. And our specification, our logical specification, is essentially that as a human, you can input the goal region for that robot. You can say, go to region 1 or go to region 3, and you can change your mind all the time, right? Even when it's currently moving somewhere, you can say, oh, no, 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 go to the other region. And there are certain things it has to take care of, right? So here in this upper right region, only one robot can be at a time. So if the other robot is there, it has to go to this region 2 to ask that robot to leave, and only then it can enter. And we showcase this effect of a human in the loop that invalidates transitions by this region 4 here, right? So if a human goes everywhere, it shouldn't go there, but we exemplify this by this region 4 here. So I show you a video on this, and I try to explain what's going on. So the human said, go to region 1. The robot realizes, oh, there is another robot there. So it's first going to region 2 to request that robot to leave. Now this robot is leaving. It's realizing that it's left, so it's now going to that region. And now the human changes its mind, and it says, oh no, now the robot is coming back. So it has to go elsewhere. It decides to go to region 2. There are multiple options, right? So it decided to do this. And then the human says, oh, now go to region 5. So it goes, tries to go there. It realizes, oh, there is a human here. So now it has to go back, because it first has to ask this robot to leave. Now it's going through here, and then going back to region 5. And now the human is telling it again to go somewhere else, yes, to region 4. And now it's realizing it doesn't have any option, right? It can just stay there. So it stays there and waits until the region becomes empty. Now it goes there, and then the human is mean and goes there. And now there's no specification, so it goes to region 2, because this is a favorable region because it allows it to do most of the things. And what you haven't seen here, I had another video, but I don't have time to show it, is that the human can change its mind, right? So while it's going to region 3, it can say, oh, wait a minute, go to region 5, and it immediately reacts to this, as it immediately reacts to the other robot moving or the human being in the scene. So if you think about how this is done, so I have turned around the picture to show you that the symbolic control is on a higher level and physical control is on the lower level. So really the symbolic controller reacts to these symbolic observations where the robots are, where the humans are, and so on. And that generates an objective for the lower physical control loop. And then the lower physical control loop also changes the context, which might not be so obvious, but when the robot is moving, then it's also moving to a different region, and that is changing the context, because then it would be together with another robot or together with the human and so on, right? So we really have a feedback loop here, here, and here. So let me give you just a little bit more detail on how we do it, and if you're interested, come talk to me after the talk. So what we do, we use our template synthesis on top. We essentially, here we really we really take the reactive synthesis approach. We take the logical specification, we turn it into a two-player game. with the standard methods, and we compute strategy templates. The nice observation is that these templates share a lot of similarity, or they're essentially reach while avoid objectives, because they localize all the progress you need and all the safety that you have to take care of. They're essentially reach while avoid objectives. And reach while avoid objectives are extremely well studied in control, okay? And especially there exists different techniques, but one that I like a lot is control Lyapunov functions. They're a bit hard to compute, but what they essentially allow you to do is they allow you to do a region that you need to avoid in your continuous state space, and a target that you get attracted to. And what you have to keep in mind is that all these things can be dynamic. So this A can be another robot that is moving, and this control Lyapunov function generates a repellent force to that other robot, and it dynamically avoids it just naturally by being repelled from it, from a lighter measurement. So this is what we're also using. And also this target can be moving. It's just an attractor force, like a magnet, that you can move around and the robots get attracted to them. And of course, if you allow moving obstacles that you don't model, these red region can get in between you and the green one, right, preventing you to make progress. So we can only certify safety if we have dynamic environments with disturbances we haven't modeled, but we can, be optimistic in terms of progress, in the sense that, humans moving around will typically go out of the way, and you will eventually be able to reach there, right? So this is a very powerful low-level control mechanism that naturally integrates with templates, and you essentially get one such function for each state, right? So if you get an input, high-level input, your context changes, that changes the Lyapunov function-based controller that you are deploying. And what's really critical, and what I will not talk about, is that you then have to lift these progress that you induce by the Lyapunov function back into the game, because otherwise you cannot allow the environment to take actions while you are moving. Okay, that's a bit technical. And then we need solution algorithms that can handle these progress assumptions efficiently. And Irmak, my students, will talk about one such algorithm tomorrow, and I will not touch upon on this, but we have ways to deal with this efficiently, and that then gives us a hybrid controller. Okay, so this is kind of the whole story, and it uses templates here, and the really cute observation is that they are kind of nicely integrating with control methods that already exist. Okay, so this was what I wanted to say here. Let me very quickly touch upon distributed control, because here I also feel that this viewpoint, this control viewpoint, adds a different angle to the discussion, because these are just symbolic control loops, right? And this has been tackled in reactive synthesis, but I would claim that if you have this control context where the physics give you a game graph, the problem becomes significantly easier and still extremely interesting to look at. So again, we are discussing this problem. Let me open this up for you. So you have two symbolic control loops. You want to synthesize these two controllers here, and you have the symbolic context that's different for these two different agents. And again, you can think of this as a drone example, where now you have two drones that are running an automatically synthesized controller. And what we essentially would like to do is, if you think about an environment where this purple robot, for example, needs to go between these locations, and the blue robot just has to check these two rooms. So it's essentially just sitting in this door, going back and forth. Then these two robots have, first of all, many different ways of fulfilling their task. And they just need to be aware of what the other needs in a very, very restricted context, right? So the blue robot needs to be aware of the fact that the purple one needs to pass. And usually if you're designing these controls, if you know that if someone is approaching you, they should pass, they should be allowed to pass, then you can synthesize this blue control in a way that it's aware of that, right? And similarly, for the other robot, that it knows that it's good to wait for this robot to leave because it promises to leave if it gets a chance when you're arriving. So this is what we try to do. We want to synthesize controllers locally and synthesize a contract that essentially implements this, like the minimal necessary cooperation between these robots in these scenarios. And because we have been talking about this problem, this very simplified maze problem so much, let me use it again to illustrate this, right? So we have these two robots, and now it's not just this one that we're synthesizing a controller for, but both of them. And remember, the physics already give us the game graph, right? And the game graph is similar as what we discussed before, right? So let us first look at this and these two robots have different objectives. Let's say the blue one needs to travel between these cells infinitely often, and the purple robot between these cells infinitely often. So let's look at the problem from the perspective of the purple robot. It only knows its own specification, okay? And if you stare at this, you see that if you use classical reactive synthesis, you will realize it's not realizable. Why? Because if you don't know anything about the blue robot can just put itself here and stand there forever, and then there's no way you can fulfill your specification. Or it puts itself in one of these cells, okay? So this wouldn't work. And now what we want to do is we want to generate, or we want to tell the other robot to help us, right? So one assumption you could say that would help you, that would render the problem realizable, is tell the other robot never move to the middle. That is definitely fine, but it's very restrictive for the other robot, because then the blue robot can't do anything, right? And this is not necessary, because the only thing you need is that this passage is going to be free always eventually, okay? So the most permissive specification that you want to give is always leave the middle again, because then I can pass, okay? And I don't know what your other things you are doing, whether you're charging in the middle, whether, but I want to make sure that you're going to leave again. And this is what we call a permissive assumption. And then we want to add this, we want to communicate this permissive assumption to the other robot. So now the other robot looks at the problem and tries to find a controller, and it will generate another assumption, and that goes on and on and on. And this process we call negotiation, and please keep in mind that this is in the offline synthesis phase. So while I'm synthesizing a controller, I'm negotiating. And then I reach a contract, and then I deploy that contract, and at runtime there is no more negotiation. I just, use my contract. Okay? So what do we need for negotiation? We need to extract these permissive assumptions. We have to adapt strategies locally to realize that step, and we have to make sure it terminates. Okay? So let's start with the first one. And the observation is incredibly simple, because we want to build these permissive assumptions. We have our game. We now look at it from the perspective of the purple robot, and it wants to put assumptions on the other player. Now notice, if you know games, this is it's a cooperative setting, but we also have done this for rational adversarial settings, you can do all that. Here, just assume for the purpose of the talk, it's cooperative, right? So I know that if I tell the other robot to act in my favor, then it will do that, but I want to use that cooperation as little as possible. So I want to just tell it what's really needed for me. And if you look at this, then you essentially see that you can synthesize a permissive assumption template, not a strategy template, but you essentially synthesize a template for the other player that tells it, oh, this is really bad, like if you do that, then you will violate my specification because I don't want anyone to jump on me, but if you do this or that, that's fine with me because then I'm able to move, okay? And this is done in the same way as strategy template synthesis, just for the other player. right? And this gives you, actually, in this setting where you assume everything is cooperative, you can prove it's maximally permissive. So it's the most permissive assumption that you can put on the other player that retains as much cooperative strategy profiles as there exist. And then we communicate that assumption to this other robot, and know what? Now we just compose strategy templates, because this other robot has computed its own strategy template, the blue one. Now it gets a strategy template from the other one that tells it what it should help with. And then this is just incremental synthesis. I take the combination of it, right? And of course, we can have a conflict, and then we need to resynthesize. But again, this rarely ever happens if you look at benchmarks. And so what you really do is you use this strategy template synthesis, but on both players in a cooperative setting, and then you communicate the assumptions to the other players, so they keep their specifications private, but they all both operate over the same game graph. That's why it works, and this is also why it terminates, okay? It only terminates because you never change the game graph, and both know that game graph up front. Okay, but still, what is nice about it is, so it's very expressive, so you can handle non-zero sum parity games, and you can use Salonka type algorithms to make it efficient. You only get, everyone keeps their strategy private, and you still get a decentralization at runtime. So once this thing has terminated, and it truly terminates, everyone has their strategy profile, their strategy templates, and you can still adapt your strategy at runtime as long as you make sure that you comply with the strategy template. So it's very robust, and you can do whatever you want. You can charge, you can avoid a human and whatnot, as long as you retain the strategy template, right? And this is why this is very interesting for control applications. Okay, so let me summarize what I have said so far. So we have developed this idea of permissive strategy templates. I've shown you how we used it for physical and logical control, and I've shown you how we used it for modular strategic control for cooperative settings. We have also recently used it to improve solvers for infinite state games. So there we use it over an abstraction where the templates tell you where you have to spend your energy trying to accelerate over infinite state spaces. And then we have used a novel solver by Raina and her student that can do this very efficiently, these accelerations. And by putting templates on top, we could vastly scale to much larger instances because you don't have to spend your energy in regions where it's not needed for the specification. Another thing we did, as I said, so here we had fully cooperative settings. We can also deal with rational agents and equilibria. And this is, I find this very intriguing because you can essentially use this concept of equilibria to define different modes of interaction of agents, but what you get is a contract in the end. And then you don't have to assume any agent to act rationally anymore at runtime. They just have to comply with their strategy templates. And that's kind of a novel way of looking at it. Of course, you need the game graph to be fixed and known up front, also here. Okay, so this is what we have done. And before I conclude, let me address the elephant, because I have been claiming to talk about trustworthy autonomy for almost an hour now. And I have not talked about data, I have not talked about machine learning, and I have not talked about artificial intelligence. So where is the elephant hiding, right? You know what? Everywhere. There are tons of data-driven methods in that scheme that are used extremely successfully, in particular in this lower level control loop. Why? Because there is a long history of adaptive control, almost half a century long history, on how you adapt controllers to data you gain over runtime. And with machine learning, this has been lifted to yet another level. And this is why we have running robots, and this is why we have Boston Dynamics dogs and so forth, because you can really, really amazingly integrate learning and data inside the control loop by backing it up, making it trustworthy by, half a decade of research on control. We can use it to predict the physical behavior, the physical dynamics of other systems in your environment. You can use that to adapt to it. And you essentially, in the systems we are running today, you have neurophysical control loops underneath. And if you go up the hierarchy, then you can handle safety objectives. And this is, I would say, the prominent research topic these days, how to back up these neurophysical control loops with symbolic safety objectives, right? If you detect a human, you don't run it over, right? If there's a car, you don't run into it, right? And this is extensively done at completely a different community. You can go to reactive synthesis, and we have transformers being trained on the classical reactive synthesis problem, where I give you a specification, you tell me whether it's realizable, and if it is, you give me an implementation, and then I verify this to make it certified. So this exists, but there is no physics and no assumptions there. And then you can use it to make symbolic observations, right? You need deep neural networks to even figure out whether there's a human in your scene and so on, to use physical classification. And there's a lot of also research on how to make sure that these neural networks that generate these observations for you, even for safety objectives, are correct in the way they should be, so that your controller architecture works correctly. But if you think of this high-level control loop, the symbolic control loop, I'm not aware of much techniques that are able to take learning techniques inside the loop for high-level reasoning that is for long, for this long-scale, reactive and not just planning, right? So really the reactive way of dealing with this. And I'm personally, of course, I'm a control person. I love feedback, right? But I would claim that we need neurophysical symbolic control loops to back up all these amazing techniques also for robotics that use transformers and so on, to make them physically grounded, to make them integrated with these amazing concepts from control, and to really push autonomy up the control stack. And this is all I wanted to say. Thank you for your attention.
Thanks a lot, Anna, for a wonderful talk. We have time for questions. So I see 3 hands. Let me start from that end. Anna, looking up.
Thank you for an amazing talk. So what do you think is the main challenge of incorporating these learned controllers, when the control is a neural network, for example, into the symbolic loop? So why can't we take the same great framework of the contracts and just put a neural controller there?
So I think the problem is, okay, let me address this question in 2 ways. I think most of this reinforcement learning type architectures that we have are very, are similar to low-level control in the sense that they're instantaneous, right? They adapt instantaneously. And the challenge, if you have more LTL type objectives, is that they're long horizon, right? And they're over somewhat unterminated behavior, right? And that requires you to localize what you have to do in the future. And this is what we do with templates, but they are model-based. So to me, it's like in control, you have model-based design and you have data-driven design. And what works well is when you combine them. Okay, but you have to combine them in the loop. In the higher level, we know how to do it model-based. we somewhat know how to do it, well, not really, but somewhat, if we only do data-driven, and this is all these amazing robot videos you get from robots washing dishes and so on, right? You train a transformer, and then it spits out a plan on how to do it. But I think the challenge is really how you integrate model-based and data-driven, right? Because it always means that in this reactive synthesis world, your game graph is changing in weird ways, right? Going back to Orna's talk, she was talking about, you know, history determinism. And it's not just that, right? I just have a limited past, a limited future where I might know what's going on from my data. How do I do this? What type of specification languages do we need? What type of, you know, models we need? Because we kind of see in the control context, it's not so complicated. Typically, things can't prevent you, you know, it's typically not the case that you have to know a lot from the future to adapt your strategy, right? Also in autonomous driving, you usually find a way, oh, then you take the other intersection right, it's gonna be fine, right? And I think we need a shift in how we think about these problems in terms of, you know, the models, and in terms of the specification languages. How do you spell out these characteristics that we kind of intuitively know, and still use this amazing framework of tools and algorithms that has been developed for also half a decade in reactive synthesis, and how do you bring it together? I think it's an amazing, theoretical challenge.
Yes, it is. Thank you.
Okay. One question I had was your environmental assumptions. You kept, and it was in your examples, it was clear that, you know, the environment sometimes had to cooperate, not all the time, but at least once in a while. Do you use fairness assumptions on the environments, or do you actually formalize them?
So we do have work on that, but I didn't touch upon that. So here, so the example I showed, it's essentially, so you can interpret the template that you put on the environment as a fairness obligation, right? You say, do whatever you want, but I want you to take these actions fairly, okay? And you can do that, you can decide when you do it, but you have to do it, right? We have other work where you say, this is on fair games, this is what Irmak is gonna talk about tomorrow, where you say, okay, I want all the agents to be fair in addition to their objective. And if you have one agent being fair, then and your fairness is local, so this is the crucial point. So if your fairness is local in the sense of a template, then all works, you get very efficient algorithms. But if your fairness is not local, it's more of a street type, then immediately your complexity blows up. I mean, you have to immediately do it. And the problem is, I mean, I don't know how much we can take this offline, but as soon as you take products of automata, local fairness becomes street. And this is very annoying, but luckily there is a different type of fairness that you can use. That's not my work, it's Nejmi Ossei's work originally. It's called progress groups. And we have formalized it for more powerful specifications and so on. And then you can show that again makes it, I mean, you can enforce fairness, that is easy. I mean, that doesn't blow up your complexity if you want to use it in synthesis. But and if you have fairness on both players, then it becomes very interesting and theoretically extremely hard. But yeah, we can take it offline.
Cesar.
Yeah, so I have two questions. So the first one is insisting on Srujan's question. What if the environment really cheats, even on safety stuff? What if the environment is cheating and there is an assumption violation, like a big one on a safety part? So for example, your game graph is not modeling properly the actual world for whatever reason. The wind is blowing too strongly. Then I guess if you do reactive synthesis, well, you won the game because your assumption is violated, so everything is great.
Yeah, but I mean, if the wind is blowing too hard, right? I mean, the thing is, it depends on what you look at. And I think, so if you have a physical control loop underneath, then the wind is blowing too hard will trigger, all your safety mechanisms on your lower level feedback controller that makes sure you're landing properly or you're adapting to data, your feedback controller. I think, so this is usually the case when I give this type of talk, that ultimately you would like to have this setup where you have a distributed symbolic control that's backed up by low-level feedback controllers that are also interacting. We are not there yet, right? I only showed you the symbolic layer and then the hierarchical layer for one agent, right? So in this framework that I discussed about this one, you assume that the robots fulfill their contract. And that's what your certification relies on. Here you don't. Here you don't. Here you say they're all selfish, right? But they're only selfish, they will only harm you if that goes into the way of their own objective. And you know these objectives up front, then you use that, right? And then, if there's a possibility of another one violating your safety specification, then you will incorporate this. But deploying the wind type, I would always deal with in a lower control. I would not lift this up to the symbolic control there. And I would then have a mechanism that says, where the lower level controller says, oh, there is a problem, there is a fault, I'm going to landing mode, and that will be a symbolic action that would be taken care of in my symbolic control mechanism. But I would never try to deal with that in the higher level. But this is because I'm a control person, and I'm like, if the wind is blowing, that's a low-level control problem. I don't know if this answers your question.
I have a second question, if I may.
Yes.
Okay. So
Yeah, quick one.
So in the reactor synthesis part of the talk, you were using like Boolean classical LTL reactor synthesis somehow.
Yes.
But modern results, you can incorporate a little bit of the data, which may be useful in this context, right, from the physical world, in your gain graph and in the reactor synthesis itself with modular theories.
So, I mean, we have been looking at, for example, quantitative objectives like energy objectives and so on. You can build templates for that, but it's harder. For time, it's very hard. But you could, of course, annotate with features and so on, and we haven't done that. I'm not sure if you have been. I mean, we can take it offline.
All right, I think we've had an excellent session, but we're running out of time because we want to keep the next session on time. Let's maybe thank and
yeah, you can just come. Questions. Yeah, you can just come and talk to me.
I myself have 3 questions which I have not asked, but we will ask that in the coffee break and probably have more. Let's all thank Anna for an amazing talk. And coffee break. Any announcements? No. Okay.